Okay, so today we're going to go ahead and go over periodic trends. So when we're looking at a periodic table, the first thing you're going to notice is what we have, what we call groups. Okay, so groups go up and down. How do we remember that? Well, if we look at the word groups, it has the word up in there, right? Groups have similar properties, and we're going to later discover these. They have similar properties because they have similar electron configurations. So again, groups go up and down. So for example, this is group one, this is group two, group three, and so forth, all the way to group 18. Okay. Then we have periods. Periods, like a sentence, if you're reading a sentence, you read it from left to right. So a period is the same thing. Periods go left to right. So we have one period, this is the second period, third period. If you notice, the first three periods don't have anything in the D block, but in the fourth period we do. Okay, fourth period and so forth. Okay, so this is just kind of words that we got to recognize what groups are and what periods are. So groups up and down, periods left to right. Okay, so why do we study the periodic table, or why is it arranged the way it is? So just by looking at it, we should already know that it's arranged in a way that tells us about certain patterns and certain trends, and it also tells us a lot of information about how things react. Okay, so we have three main sections. We're going to break it down to further sections, but the three main sections in the periodic table are the metals, which is this large section. So almost all elements, or the majority of the elements, are metals. Then we have our metalloids, which is this little staircase here. And then we have our non-metals. Okay, so a couple of properties to note. Metals are good at conducting heat and electricity, which means they're able to move electricity and they're able to move heat through it. So, for example, if you have a metal pole and you're grabbing it at one end, you heat up one end, you're going to eventually feel that, right? And metals are malleable, which means they can be hammered into sheets. And these are just a few properties. I know you guys researched. You guys also researched them. All right, then we have nonmetals. Nonmetals are poor conductors. So essentially, the opposite of metals, they're poor conductors of electricity and heat. In other words, for example, if you're in a room full of oxygen and nitrogen, and you heat something up on the other side of the room, you're unlikely to really feel that heat, right? Because they don't conduct, they don't move heat through it very well. Metalloids are kind of in the middle. They're also called semi-metals. They're used a lot in electronics because they have they conduct electricity and heat at a medium capacity, so they're kind of in between these. Okay, so our first group here is our alkali metals. So our alkali metals are very reactive, and they react by losing one electron, and we'll go over why that is. But when we're studying any metal and we're studying how it reacts, every element reacts to have a stable energy shell. In other words, to have a full energy shell. So everything wants to have a full outer shell. So all of these in this first group have one valence electron. So this whole thing has one valence electron. Okay, so let's look at, for example, let's look at the Bohr model of lithium. Well, lithium has a Bohr model that looks like this, right? I would have one shell, two shells. In this would have one electron, two electron, and then the outside would have one. Okay, so why does it lose one electron? Well, if it were to lose this electron, if we were to lose this electron, what would happen is we would only have this shell, which has two electrons, and that's considered full. So if it loses one electron, it becomes full. Okay, and that goes on for the rest. So sodium also has one on the outside. If it loses that one, it has eight, and it becomes full. Okay, all right. Let's move on here and look at another example. Okay, here we have our alkaline earth metals. This is the second group. They are also very reactive, and both of these groups, both the first and second group, react with water, and they react by losing one or two electrons. So these react by losing two electrons. They're less reactive in the first group, though, because they have to lose both of them to react, whereas the other ones, the alkali metals whereas the alkali only have to lose one, but these have to lose two. Okay. Okay, so let's look at why they're losing two. So let's look at magnesium. Let's do that Bohr model. It might take us a while, but I think it's kind of worth illustrating that. So we have, let's go, we have 1 energy shell, 2 energy shells, 3 energy shells, right? Let's get red here. So we have 1 electron here, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we want 12 though. So we have 2 on the outside. All right, so if we lose these 2 electrons, if we lose this electron and we lose this electron, what ends up happening is this energy shell here, it has 8. So that's full. So things react to become full. In other words, to become stable. Okay. All right. Let's go ahead and move on here. And all of these here have 2 valence electrons. So that trend continues all the way down. Everything here has 2 valence electrons, whereas everything here has 1. Okay. So if we're doing a Lewis diagram, now we don't have to draw the Bohr model first. We can just draw the Lewis model right away because we know if it's here, it's going to have 2. Okay. So for example, barium, I can easily draw the Lewis diagram. I know it's there, so it has 1, 2. I don't have to draw the Bohr model first anymore because I understand the trend. All right, next slide here. Then we have the transition metals. The transition metals are this entire group here. It's a lot of the common metals that you hear of, such as iron, copper, nickel, silver, gold, and so forth. So this whole group here, that whole D block, those are our transition metals. The main thing you have to remember about this group is that they do not follow the valence electron trend. Okay, everything here has 1 valence electron. Everything here has 2. These do not follow the trend. We skip these. We go 1, 2. These have 3 valence, 4, 5, 6, 7, all the way up to 8. These have 8. Okay, so ignore that 0. Just keep that in mind. Because if you don't remember that, you're going to get confused. Okay, let's go ahead and move on here. Now let's start at this far end. So we just went here. Now let's work our way from the noble gases, which we already know, right, to this side. So the noble gases were some of the last elements that were discovered, because often when we were looking at elements, we discovered them by how they reacted with other elements. But the noble gases are actually non-reactive. Okay. Well, why are they non-reactive? Well, we've been saying that everything wants to have a full outer shell. Well, the noble gases, they already have a full outer shell, right? So this has 8, this has 8, helium has 2, which is also considered 4 if we have for the first energy level. So all of these are gases and they all have full outer shells, therefore making them non-reactive because they're basically already happy. They don't want more electrons. They don't want to lose or gain electrons. They're happy. Okay. All right. So basically, everything wants to be like a noble gas. That's how everything wants to react like a noble gas. Now we have the halogens, group 17. Okay, all of these have 7 valence electrons. So remember, for following the trend, we go 1, 2, skip 3, 4, 5, 6, 7. So it's almost like you can just ignore that 1. So these have 7 valence electrons. They're called the halogens. They're group 17. They're very reactive, and they react actually by gaining 1 electron. Okay, so let's think about why that is. So if I look at fluorine here, fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. Well, there's 2 ways it can become stable. It can lose all those 7 electrons and therefore become stable. Or it can gain 1 electron. If it gains 1, now it has 8 and it's stable. So in terms of energy, you can just kind of think about it. What do you think would be more favorable in terms of energy? Gaining 1 electron or losing 7? So obviously gaining 1 is going to be a lot easier than losing 7, right? So that's why it reacts in that manner. And because it only has to gain 1, it makes it very reactive. Okay, so that's the way things react. This is just a quick review. We kind of know this, right? We have our S block, our D block, our P block, and our F block down here. And these correspond to the type of electron orbitals that those elements occupy. Okay, so let's go ahead and go into our trend here. Ionization energy is the first trend we're going to explore. So what is ionization energy? Okay, ionization energy is the energy needed to remove an outer electron. So we've gone over this already, right? So energy needed. So if I have a atom here and I have a valence electron, the energy needed to take this electron off is going to be my ionization energy. So if it takes 10 joules of energy to take it off, my ionization energy would be 10 joules. Okay, so let's look at the trend here and see whether or not this kind of makes sense to us. So when we go to the right, our ionization energy goes up. In other words, it's harder to take off electrons. Why? Because when we're going to the right, we keep adding more and more positive, right? So here we have 3 protons, then we add more positive, more positive, more positive. So every time we go to the right, we keep adding more and more protons, so more and more positive charge. So because my positive charge goes up, it causes an increase of electrons. An increase, it holds the electrons tighter, not allowing them to be easily taken off. Okay, so when I go to the right, I increase my positive charge. Okay, and that makes it harder to remove the electrons. So it makes it more difficult to remove the electrons. Okay, now that makes sense, right? We have more positive, more positive. So they're holding the electrons tighter, so it's harder to take them off. All right, when we go down, another way to think about this, although I like to think about it not as increasing going up, but rather when I go down the table, my ionization energy actually goes down as well. In other words, what does that mean for ionization energy to go down? All that means is that it takes less energy to remove an outside electron. So it's easier to remove an outside electron. Well, why is that case? Well, when we're going down, we already know, right? We're adding energy shells. The first one has 1 energy shell. The second one has 2. And then the so forth, 3, and so forth. So basically what's happening is, remember, the positive charge is in the middle. The positive charge is in the nucleus here, right? The positive charge is in the nucleus. So as we go down, as we're going down, we're adding more and more energy shells. So the ability to get electrons becomes further and further away because we're getting electrons are all the way in the outside, right? So the ionization energy refers to taking away that outside electron. So if we have an outside electron, it becomes easier and easier to take it away because it's not that attracted anymore because it's so far away from the nucleus, right? And as we go, we'll get further and further away as we go down the table. So ionization goes down because we add shells, causing the electron to go further from the nucleus, therefore easier to take away because it's not that attracted anymore, right? Because the thing that's holding these electrons is that positive charge. Because remember, opposites attract, right? All right, so let's recap. When we go to the right, more positive charge holds electrons tighter, so it's harder to take them off. When we go down, we add shells, so the negative charge goes far away, so it's easy to take off, causing a low ionization energy. Okay. All right, let's go ahead and keep moving on here. All right, atomic number, this is a pretty straightforward trend. When we go to the right, we add a proton. When we go down, we add protons as well. Okay, that makes sense. All right, Coulomb's law, we've kind of already reviewed this, right? It basically states that opposites attract. That's the first thing it states. So if we have a negative and we have a, let me actually draw that a different color here. So if we have a negative and a positive, then they are attracted to each other. If they're far away, then they're going to be less attracted. So for example, something like this and something like this are not going to be that attractive like these are. These would be very attractive, whereas these would be barely attractive because they're further apart. Okay. Also, the amount of charge matters. If I increase my positive charge, then the attraction becomes greater. And if I increase it even more, it becomes even more greater. That's all Coulomb's law says. Things that opposites attract, that's the first thing it says. The second thing it tells you is that when things are close, they're more attractive. And the third thing it tells you is that as the charge increases, so does the attraction. Okay, so we've gone over that. I just want to bring it up again because we're going to use it throughout this. Okay, let's go ahead and look at these trends. So first, we got to understand why atomic size increases as you go down. So when we go down, obviously, as we can see in this chart, things get bigger. So let's go over why. So we know that when we go down, we're adding energy shells, right? So we add every time we go down, we add one energy shell, then we add another energy shell, then we add another. So that's why atomic radius decreases when we go down, because we add shells. That's pretty straightforward. I think that makes sense. Okay. However, when we go to the right, most people think because we're adding more and more protons, we're going to get bigger when we go to the right. But that's not the case. Look, as we go to the right, things get smaller. So that's actually not very intuitive, and it almost doesn't make sense, right? However, the reason things are getting smaller when we go to this side, because remember, all of these things have the same energy levels, right? This has two energy levels, this has two, and so forth. This has three, and so forth. So energy shells don't play a factor in the fact that they're getting smaller. They're getting smaller because when we go to the right, we add protons, right? We add, in other words, positive charge. So we add protons. So what are those protons doing? Because remember, atomic radius is the size from the middle all the way to that outside shell, right? So when we add protons, that's positive. Positives and negatives attract. So what does it do to the outside negatives? It actually pulls them in, it pulls them closer to the center, and it makes the atom smaller. So when you add protons, it actually pulls electrons in. Sorry, it's kind of hard to write with this. Okay, it pulls electrons in. So quick recap, when we go down, we get bigger because we add shells. When we go to the right, we get smaller because the protons pull the electrons in, causing things to be smaller. All right. So we got about one more trend here before we finish up. Let's see here. Okay, electronegativity. This is our last trend. What is electronegativity? Electronegativity is how attractive something is to an electron. In other words, something that's very electronegative really wants electrons. If you're not electronegative, then you don't really want electrons. Okay, this is very similar actually to the ionization one. So when we go to the right, we become more electronegative. When we go to the right, we have an increase in electronegativity. Why? Well, why would I be more attracted to electrons when I go to the right? Well, because I'm adding positive charge. That's why, because I'm adding protons. That's why I'm more electronegative. Okay? So fluorine is the most electronegative atom that we have. It really wants electrons. When we go down, we actually become less electronegative. We become less. So in this chart, the things that are popping out are the things that are more electronegative. Less electronegative. This is the one that might not make super sense, right? Like, why is it that when we go down, we're not that attracted to electrons? Because cesium has way more protons than fluorine. But why is it not more attracted to electrons? Well, when we go down, we keep adding energy shells, right? We keep adding energy shells. So cesium would have it would have a bunch. I'm not going to draw them all, but it would have a lot of energy shells, right? It's a little sloppy there. It would have a lot of energy shells. So what happens is when we go further and further out, it's not the nucleus is so far away. So the positive charge here is so far away from the electrons that it no longer really attracts them. So when we go down, we become less electronegative because we add energy shells. Things down here the electrons are so far away from the nucleus that they're not even that attractive. Okay, so quick recap again. As I go to the right, I add protons, so I become more electronegative. When I go down, the negative charge gets so far away from the nucleus that it's not very electronegative. All right, then your other question might be, why are these noble gases just flat? Why are they not electronegative at all? Well, these are the only ones that don't follow the trend. Okay, let's think about why that is. Well, electronegativity means you want to attract an electron towards you. Well, these all have full shells, so they don't want electrons. They're already happy. They don't need any more. That's why these are not electronegative at all. They don't follow this trend. Okay, so that's pretty much it. And we'll go ahead and do some practice, and hopefully it starts making a little bit more sense.